Hello everyone, my name is Brant Kudrowski and this organic chemistry video covers alkene nomenclature part 2. This is how to name stereoisomers and some common names. Alkenes that exhibit stereoisomerism require additional nomenclature to describe them. Here's an example of an alkene. It has the longest carbon chain indicated here by the highlight and numbered from one end to give the lowest possible number to the alkene. It would have these numbers. Under IUPAC naming, its name would be pent-2-ene, or under the older rules, 2-pentene. The thing is, this molecule has a stereoisomer. I can tell because the groups on the left carbon are different. Hydrogen and methyl are different from each other, and the groups on the right carbon are also different. Hydrogen and ethyl group are different. So there's a stereoisomer of this molecule, and that is shown here. It has this longest carbon chain indicated by the yellow highlight, and this numbering of the chain. And under IUPAC rules, it would also be named pent-2-ene or 2-pentene. So these molecules have the same basic name, but they're different in their arrangement of groups in three-dimensional space. They're stereoisomers of each other, and we need to have names to distinguish them. Disubstituted alkenes like these can be distinguished using cis and trans prefixes. To do that, draw a line bisecting the C-C bond through its carbon atoms as indicated by the red dotted line shown above. Then, when the R groups are on opposite sides of this line, use the trans prefix. In the upper example on the left, the methyl group and the ethyl group are on opposite sides of the dotted line, so this would get a trans designation. Trans and cis prefixes go out in front. They're usually in italics, and they're separated by a dash from the rest of the name. So this would be trans pent-2-ene or trans 2-pentene for naming the molecule on the left. The molecule on the right is different. It has its R groups on the same side of the line, and in this situation, you use the cis prefix. So the molecule on the right would be cis pent-2-ene or cis 2-pentene. Just a reminder, not all disubstituted alkenes have stereoisomers. Here's an example of a molecule that doesn't exhibit stereoisomerism. Here's its longest carbon chain highlighted in yellow, and numbering the chain from the end to give the lowest possible number to the CC double bond gives this numbering. And the name of this molecule is simply 2-methyl-but-1-ene under the newer rules, or 2-methyl-1-butene under the older IUPAC rules. There is no need for cis or trans here. This name fully describes the molecule. In fact, it wouldn't be appropriate to call this a cis or a trans molecule because those terms don't apply. They're only used for stereoisomeric alkenes. This slide introduces the EZ nomenclature system for alkenes. Cis and trans prefixes only work for disubstituted alkene stereoisomers. They're not well defined for other types of alkenes. Here's an example of a more highly substituted alkene that doesn't name clearly under cis and trans. Here, the two methyl groups are cis to one another, but the methyl group and the ethyl group are trans. Cis and trans would be ambiguous for this molecule, so we need a different system that unambiguously assigns the positions of these groups. The prefixes E and Z work for any alkene. The names come from German words. E for entgegen means opposite, that would be like trans. The term Z comes from the German word zusammen, and that means together. That would be like a cis arrangement. To assign E and Z labels, you first need to assign the groups on each C double bond C carbon a priority of number 1 or number 2 based on R and S naming rules for stereogenic centers. If R and S nomenclature and priority assignments is a little fuzzy, you should definitely go back and review that concept because E and Z nomenclature requires that you know how it works. We'll go over it in this simple example just to describe how it works in brief detail. Look at each carbon atom of the alkene and assign groups a priority. The left carbon of the alkene has a hydrogen atom attached as one group and a carbon atom attached in the other group. It's very easy to assign priorities as carbon is a heavier atom than hydrogen. So we can assign a number 1 priority to the methyl group and a number 2 priority to the hydrogen. The atoms attached to the carbon of the alkene on the right include a carbon atom and a carbon atom. We have a tie. So in this situation, we need to look one step further along each chain to identify atoms attached to the circled carbons to break the tie. On the upper group, we have indicated by squares a hydrogen, and a carbon atom. And in the lower group, we have indicated by squares a hydrogen, and a hydrogen. So in this case, the upper group has a higher priority because one of its atoms is a carbon, which has a higher mass than hydrogen. Therefore, we can assign these groups values of a number 1 for the upper group and a number 2 for the lower. The next thing to do is to draw a line bisecting the C double bond C bond through its carbon atoms, and I'll indicate that with the red dotted line here. And then when the high priority groups are on opposite sides of this line, it's like trans. You should use the E prefix. That's the situation that we have here, where we have our number 1 priority group on the left carbon on the lower side of the line, and our number 1 priority group on the right carbon on the upper side of this line. This would be an E alkene. When high priority groups are on the same side of the line, then you'll use the Z prefix. That's like cis. The full name for this molecule then would be, under the newer rules, E3-methylpent-2-ene, or under the older rules, E3-methyl-2-pentene. Let's work through a practice problem to get a little bit more experience with this concept. Here's a molecule that contains an alkene, and first thing we'll do is assign the longest carbon chain to find its root name. Then we'll number the longest carbon chain from the end that gives the lowest possible number to the alkene, and in this case we would start from the left side because it gives the alkene a number 4. And based on this, we can assign the root name of this molecule as known 4-ene, or 4-nonene, depending on which version of the IUPAC rules you choose to use. This molecule contains a chloro group in the 1 position, a butyl group in the 5 position, an isopropyl group in the 4 position, and a methyl group in the 8 position. Placing those groups alphabetically out in front of the root name gives 5-butyl, 1-chloro, 4-isopropyl, 8-methyl known 4-ene, or under the older rules, 5-butyl, 1-chloro, 4-isopropyl, 8-methyl 4-nonene. This is enough to describe the connectivity of the molecule, but we need the E and Z labels to properly describe which of the 2 stereoisomers we've got here. So I'm going to get rid of all of the labels just to clarify things, and I'm going to draw a dotted line bisecting the double bond to help us identify groups. Looking at the left carbon of this double bond, we'll identify the groups that are directly attached to it. So there's a carbon atom and a carbon atom. We have a tie, so we need to look at the groups that each of these circled carbons is attached to. The upper group is attached to another carbon, a carbon, and a hydrogen, which I can draw in and indicate there with a square. The lower group has hydrogens, which I'll indicate with squares, and 1 carbon attached. Between the 2 circled groups, the upper group has higher priority because it's attached to more carbons. I'll assign this group a priority of 1 and this group a priority of 2. If we go on and take a look at the lower carbon of the alkene on the right side and compare the groups attached to it, we have a carbon and a carbon atom. That's a tie, so we need to go a step further along the chain to break the tie. When we do that, we get another CH2 in the upper and another CH2 in the lower group, and we still have a tie, so we need to go a step further yet. And when I do that, I'll draw a triangle around this group to indicate the level of analysis that we're at. Here is the 3rd carbon removed from the CC double bond carbon. And in the upper example, we have a carbon that's attached to 2 methyl groups, 2 carbons, whereas in the lower, we have a carbon that's attached to only 1 carbon group. At this point, we can assign priorities to the groups then. The upper group has priority 1, and the lower group has a priority number 2. Since the high priority groups in this molecule are on the same side of the dotted line, this would be a Z alkene, and we could put the Z label on the double bond, and ultimately we can put it out in front of each one of the names to fully assign the name for this molecule. Let's go through one more practice problem. Here's a molecule that contains 2 alkenes, so this is going to be named as a diene. We'll first start off by finding the root name. That would be the longest carbon chain that runs through both of the carbon-carbon double bonds. It's indicated here with a yellow highlight. Then we can number this chain from the end closest to the first double bond, and if we start on the left, the first double bond gets a 2, and the second double bond gets a 5. The root name for this molecule then would be octane, but since it contains 2 double bonds, it would be an octadiene. The double bonds are located in the 2 position and the 5 position, so it would be a 2,5-octadiene, or under the newer rules, octa-2,5-diene. We also have a bromine in the 2 position, so it would be 2-bromo. The name for this molecule then would be 2-bromo-octa-2,5-diene under the newer IUPAC rules, or 2-bromo-2,5-octadiene under the older rules. But we still need to assign stereochemical designators to each of the double bonds because each double bond in this diene has stereochemistry. To help with assignment of E and Z on each one of these alkenes, I'll draw dotted lines through each one of them and we'll look at the groups that are attached. If we start with the left double bond and the left carbon, this carbon contains a carbon group and a hydrogen which isn't indicated. So in this case, the lower group would have priority number 1 and the upper group would have priority number 2. If we look to the right carbon of that double bond, the upper group has priority 1 because it's got a carbon attached, and the lower group would have priority 2 because it has just a hydrogen attached. Therefore, the stereochemistry of this double bond would be E. If we look at the right double bond, there's a carbon group versus a hydrogen group, so the priorities are 1 and 2 based on those two groups. And if we look at the right carbon of the rightmost double bond, we have a bromine versus carbon. Bromine is a higher priority than carbon, so it gets a number 1, and the carbon group gets a number 2. So the stereochemical labels for these for the left double bond would be E, and for the right double bond would be Z. We need to indicate which stereochemical label belongs to each double bond with a number. You'll notice here in the labels we have 2Z and 5E. The 2Z is indicating that the double bond in the 2 position has the Z stereochemistry, and the double bond in the 5 position has the E stereochemistry. There are just a few common names that we'll talk about for alkenes. These are alkenes that are commonly known by other names. The simple 2-carbon alkene is typically called ethylene. Under the IUPAC rules, it would be named ethene, but almost everybody calls it ethylene. This is an important one because it's the starting material for an important polymer called polyethylene that you'll see in many different things, from shampoo bottles to packaging material of all different sorts. Here's a molecule that has a 3-carbon chain, and it's commonly referred to as propylene. Under IUPAC rules, it would be propene, but most people refer to it as propylene, and it's an important starting material for the polymer polypropylene, which is commonly used in a lot of food packaging materials. Then there's this molecule, which contains a double bond with a phenyl group, a benzene ring substituent. This is called styrene. It's the starting material for an important polymer called polystyrene, which goes into many things, including packaging and styrofoam insulation material. Alkenes can sometimes be named as groups as well. In situations where you have a carbon-carbon double bond as a group attached to, say, a ring, this would be a methylene group. In situations where you have a double bond attached to a molecule and the double bond just contains hydrogens, this is called a vinyl group. And then another situation that turns up a fair bit is a molecule that has a CH2 attached to a double bond attached to some other molecule, as indicated by the squiggly line here, and that's called an allyl group. This isn't an exhaustive list. It's just a few examples that you'll come across quite frequently. If you found this video useful, check out the next one in the series or watch the prior video. And consider subscribing to my YouTube channel. My name is Brant Kudrowski. Thanks for watching.